Hello everyone. In this lesson we will look at self-attention, which is the most important concept in the transformers architecture. So let's begin. First of all, what is self-attention mechanism? So this mechanism allows the model to weigh the importance of each token in the context of entire sequence. So if we have, let's say, 5 words in a sequence, and let's say we want to know which words are how important in the context of word W2, then this self-attention will kind of find out the relationships with all the words. Similarly for all the other words like W1 with respect to all others, and these edges will have different weights, and that will be the final aim where we will be calculating the attention matrix for all the words in the sequence. So it helps the model to understand the relationships between the tokens in the input. And it is key to transformers' ability to handle long-range dependencies and complex relationships between words, and we will see how that works. So it helps to also generate coherent and contextually appropriate text, since the understanding of context in which a given word in the sequence is used is significantly better due to this self-attention mechanism. So first of all, what are the learnable parameters when we look into this self-attention? So just to give some info, so when we later look into transformer architecture, so we will have this encoder and we have also decoder. So within encoder and decoder we have multiple transformer blocks which consists of self-attention and then some fully connected or networks, and also some skip connections and some addition and layer normalizations. So this self-attention comes in here. It also occurs at multiple places within the decoder, and these encoder and decoder are themselves repeated multiple times. So input to encoder is so these sequences W1, W2, so these are converted into tokens by a process called tokenization, and we had already seen tokenization and various different tokenization methods in our earlier lessons. And then these token IDs are converted to embeddings, which are fixed size for each token, let's say 512 dimension as in the original transformer paper. And so then these embeddings are mixed with positional encodings, and which is of the same dimension, and then it goes to the encoder. So these self-attentions are used within the encoder as well as decoder. We will see all of these later. So now what are the learnable parameters within self-attention? So we have weight matrices, and these are called query, key and value weight matrices. So what is the dimension of these? So we saw that let's denote a sequence by sequence I by, let's say, xi, and this sequence is nothing but a token, and so xi denotes a token, a word in the sequence, ith token, and it will be of dimension de, e for embedding. So in this example we saw 512, so it will be 512 some values, 512 values. So once you multiply xi with these weight matrices, you get what we call query, key and value. So xi is d cross 1. So the second dimension of these should be DE. So the dimension of WQ will be DQ cross DE. Similarly here it will be DK cross DE and DV cross DE, because we are multiplying with xi, which is of dimension DE cross 1, where D is the number of elements in the embedding of a given token. And so this query is nothing but WQ times xi is query I. So it will be done for all the words in the token. So let's say T denote sequence length or number of tokens. Then this WQ times x1 will give you q1, WQ times x2 will give you q2, and so on. WQ times xt will give you qt. So you can make this one vector, and so WQ times x, you can keep all the tokens of the sequence in a vector x to get q, or you can denote by capital Q. Similarly for key and value. So these are the learner parameters, these weight matrices, because these embeddings are fixed and these are not learned as a part of self attention. So these are learned separately. Now this is the input sequence embeddings. So now let's understand how this works. So first we will see a basic form of self attention, where we will not be scaling or normalizing some of the weights, but it will be very useful for understanding the concepts. So we have these tokens x1, x2 all the way up to xt. So it should be xt here, xt. So again these should be qt, kt and vt. So you multiply x1 with wq, wk and wv to get q1, k1 and v1. And let's say we are currently calculating the self attention for this second tokens in the sequence. So this same process will be done for all the tokens with respect to all other, but we are, for the time being, to understand the concept, we are just focusing on one such token. So how is it calculated is that you have this q2, k2 and v2. So current, we call it query term, or the current token. So this is calculated like, since current query is 2, second token, so we take the q corresponding to that, so q2, and take the dot product with k1 transpose and then multiply with v1. So this dot product will be a number, a scalar number, and then when we multiply by v1, which is nothing but this wv times x1, so it gets the dimension of dv cross de multiplied by de cross 1. So it gets dv cross 1. So in the original transformer, dv is equal to de, which was equal to 512. So this whole thing is of the same dimension as v1 or x1 in this case. So this q2, we will be picking this query from this query term. Similarly for here also, q2 is fixed, but corresponding k2 and v2 are multiplied, and all the way up to tth term in the sequence. So q2 is fixed everywhere. Since the current sequence we are looking at is this. The query term is the second one. So we multiply query with key of all the sequences one by one, and then with that dot product we multiply the corresponding values, and then we generate this A2. So A2 because we were looking at second term in the sequence. So this A2, or we can write A, Q2 and KV. So query term is 2 is equal to let's denote this complete thing with a shorter notation, otherwise it will be lengthy here. So let's call this A21, A this whole term as A22, and this whole term as A2T. So this will be softmax of this. So let's write the softmax A2. 2 is fixed because we are calculating A2, and then I. So this I goes from 1 to T, number of tokens in the sequence, and denoted by summation of E A to J for all the value of J, and then we multiply with Vi, and we get this A. So this term will be 1 cross 1, and then we multiply by Vi. So this whole term will have 1 cross dV dimension. So this A2 is 1 cross dV. Similarly, we calculate A1, A2, A3 all the way up to AT, and then we combine them together, write them together in a single matrix called A. So A will have A1, A2 all the way up to AT. So this we will call as attention score matrix, and it contains all the info for a given term, how important are all the other tokens in the sequence. So this is the basic concept of self attention and how is it calculated. So we did not do one thing here, that was scaling before applying the softmax. So that we will see shortly. So next we did simple multiplication there, but this will be scaled dot product. So we were doing it individually for different query. We were denoting it as Q1, Q2. So instead of that, we will combine those into bigger terms, Q, then K and V. So which will contain all Q1, Q2 all the way up to T. So we are basically vectorizing it instead of doing one by one. So we have this query, key and value. So if you see in the softmax, we were multiplying V in the end. Before that, we were taking the softmax of this A2I. A2I was nothing but so let's look at this one single term. So we were multiplying a current Q with some corresponding K, and then multiplying V. So let's write it in vectorized form. So how we will write? So let's first denote this Q, K and V. So this Q will be number of tokens times dq. Similarly, this k will be number of tokens times dk, and v will be similarly number of tokens times the dimension of this will be this matrix will be t times dv. And now we are doing softmax of qk transpose times v. But before taking the softmax, we are scaling it by and dividing it by under root of dk. So why we are doing it? So we are doing it to ensure that dot products between query and key don't grow too large and softmax gradient becomes too small for large dk. So softmax, if you remember, is a kind of generalization of this sigmoid. So it's a curve like this which tends to flatten after some large value of input. Similarly, it flattens out for very low values. So to make sure that the value does not become very large or very small, we are dividing it or normalizing it, and we are dividing it with square root of dk. So you can see it diagrammatically here, which is taken from the original attention is all you need paper. So qk matmul, which denotes this term, dot product, and then scale denotes this dividing by dk, and this mask is optional, and then we take the softmax, and finally we multiply with v, and you get a qkv. So this is a scale dot product attention. Now we had looked at self attention, but in the transformer we will use multi-headed self attention. So let's look at multi-headed self attention. So this is one self attention representation or calculation, and here what we are doing is we are keeping multiples of those. So we apply self attention multiple times in parallel. So if you see the diagram, this one block, it's denoting this block. Then you see multiple blocks are stacked in parallel. So here H denotes H such blocks in parallel are concatenated one after other. Similarly, this V, K, Q are again multiplied H times, and they are stacked together. All of these things are stacked together, and whatever was the result here, so we had a result A here for a single attention. So here we get H such attentions results, A1, A2 all the way up to AH. So this concatenate operation here, it will concatenate all of those into a single A, and then apply further operations on this. So instead of that, if you replace by single self attention, it will be just A1 will be same as A, and there will be no A2, A3. So this is how multi-headed attention works. And for each head we use different WQ, WK and WV, and then concatenate the results in the end. So next, now I think we are ready to dive into the architecture of transformers. So we will look at transformer architectures. So just to add, in the multi-headed self-attention, each head learns some different aspects of the language. So it allows attending to the different parts in the sequence in a different way. So yeah, let's see meet in the transformer architectures lesson.